This video is going to take a look at the properties of logarithms. Now that we've kind of learned how to use logarithms to solve equations, and we've also looked at logarithms as functions, we need to take a quick look at some properties that come in handy from time to time, especially if you're doing calculus on logarithmic functions. So just to review, we've got the basic exponential situation, right, where we have some base number raised to an exponent giving us the power. And if that is the case, then the inverse relationship would be with the log, that we can take the log of the power to some base and end up with the exponent. So the exponent and the power are kind of switching roles between being the input and the output. So now what I'd like you to do is if you'll pull up this sheet, the video lesson notes and examples, is take a look at items 1, 2, and 3 and see if you can fill in the blanks with either a number or an operation that would go on them, something like plus, minus, multiplication, division, or perhaps I think one of these blanks will be filled in with a number. We're using some easier numbers. You shouldn't need a calculator to do this, but you can analyze the logarithms and then hopefully fill in what you think goes in the blanks. Pause the video, take a few minutes to do this for numbers 1, 2, and 3, and then we'll go over them. Okay, so let's take a look at number 1 here. As we look at the numbers here, I think the first thing I might do is just say, okay, well, I know 4 times 8 is 32, right? And what is the log of 32 base 2? 32 is a power of 2, right? I believe if we multiply 2 by itself 5 times, okay, I think we have 2 to the 5th, we know equals 32. So that would mean the log base 2 of 32 is 5, okay? And then let's say the log of 4 base 2, right? 2 squared would give us 4, so that would be 2. And then the log of 8 base 2, that would be 3. So hopefully you looked at that and decided that the operation that needs to go between the 2 and the 3 would be a plus. Yes. So this seems kind of strange, but if we consider the fact that what we're multiplying in here, the 4 times the 8, those are like the powers, right? You take the log of a power, all right? And then when we look at the logs, right, remember the logs are actually the exponents. So we're multiplying powers here, and then this is basically saying that we should be adding the exponents. And we already know that, right? We know that 32 here can be rewritten, well, it can be rewritten as 4 times 8, but 4 times 8 is 2 squared times 2 cubed, right? And when we have, like bases, like we have here on the logs, either the same base, what do we do with the exponents, right? We add them. This would be 2 to the 2 plus 3 power, or 2 to the 5th. So that's really all this relationship is stating, is that, we need to be adding the exponents. So when you come down to number 2 now, switch colors here, we can see we have division of powers. So thinking about what we did in number 1, perhaps you're already kind of guessing what's going to happen with number 2, but let's work through it here. So we have a log base 2, 64 divided by 4, I believe, is 16, and the log of 16 base 2, right, that would be 4, okay? 2 to the 4th would give us 16. Now, the log of 64 base 2, let's see, that would be 1 more 2 beyond 32, right? So that is 6. And then the log of 4 base 2, we already said was 2. So what's the operation that should go in here? Yes, it would be a minus, right? And so once again, if we are doing 64 divided by 4, right, we're simply taking 2 to the 6th divided by 2 squared, and that would be 2 to the 6 minus 2, or 2 to the 4th. So this is, of course, kind of the quotient. We're using the quotient rule with exponents, and that's really what this is saying. Powers are being divided, so exponents are being subtracted. Okay, so let's now take a look at number 3. So let's see, 4 cubed, let's see, 4 times 4 is 16, times another 4 would be 64. right? So we've already done that one. We know the log of 64 base 2 is 6. And then that equals something times the log of 4 base 2, which we know is 2. So 2 times what would give us 6? Yes, that would be 3. And if you look at that, what's the significance of that? Well, notice the exponent up here is a 3. And it turns out that that exponent can kind of come out to the front. This is based on on the idea of a power raised to an exponent rule that we have. For instance, so we have 4 cubed, okay? Now 4 we know is 2 squared. So we have 2 squared cubed, right? And we know that when we have this situation, we need to be multiplying the exponents. So we can kind of see this relationship in the 4 cubed. The 4, of course, is 2 squared. So we basically have 2 squared cubed. We have a power raised to an exponent. And this is down here saying, well, what do we do to the exponents? Because the log is an exponent, right? And the 3 is an exponent. So what do? We multiply them. All right, so scrolling down here, we've got these 3 properties that we can fill in here. Let's see, for the first one, we were saying that the log of u times v to some base would be the same thing as the log of u plus the log of v, right? When we're multiplying the powers, we're adding the exponents. And then the second one here with the quotient is if we have the log of u divided by v, then it'd be the log of u minus the log of v, all right? All, of course, to the same base. And then the third one is if we have the log of some number raised to an exponent, what we can actually do, just kind of think of, we can bring that exponent out to the front, and it just becomes n times the log of u to some base. So while these are fairly simple properties, it's good to get some practice with them, get used to them, so that you'll be able to recognize them pretty well. So there's one more property I want to make you familiar with. And that's this one that's called the change of base property. It's really quite remarkable. Let me bring my pen over here. It turns out that the log of some number to a base, some number a to a base b, is actually going to equal the log of a divided by the log of b. And now this is the common log I'm showing here, but it would also equal the natural log of a divided by the natural log of b. In fact, it doesn't really matter what your base is as long as it's the same. It would actually equal the log of some base c of a over the log of that same base c of b. Let's just explore it real quickly with the calculator just to kind of see, because it's pretty remarkable that it's got to be true. But let's see, if we take the log, I'll just keep it simple. I don't need to keep it simple. Let's go log base 5 of let's say 85. Okay, log base 5 of 85. If I hit enter, it's 2.76. All right, now let's do a quotient, and let's take just the common log. All right, so I'm going to do the common log. I'm going to skip over and just do the common log of 85. All right, and now tab down below, and we're going to do the common log of, skip over the base there, and just do the common log of 5. And you will see we actually get the same number. And if we do this one more time and replace the common log with the natural log of 85 divided by the natural log of 5, once again, we get 2.76. And just to tease you a little bit more, let's just choose some other base. So let's just do the log of, say, 2.3, base 2.3 of 85, all right, divided by, and let's try this again, log 2.3. Now it's got to be the same base we're using on top and bottom. And then we'll have the log 5 on that, and there you go. It doesn't matter what the base is. So we usually just choose either natural log or common log because those are the most used logs we have, and it's easy to access in the calculator. Now, I know you're thinking, boys, how can this be? But let's just show. I think the easiest way is just kind of take a look at proof, and it's good to practice reading some proofs here. Okay. So we're going to start with a log of a base b. Let's just suppose that equals some number p. Okay. And if that is the case, then let's see, that would mean that b raised to the p power is going to have to equal a, right? Okay, now we need to involve both the log of b and the log of a. I'm just going to go with common log for this proof. We could turn around and do this again with natural log, but we'll just use common log. So let's just suppose that the common log of b is equal to some other number q. All right, it's got to equal some number. As long as b is positive, then we've got it. So that would mean that 10 raised to the q is going to equal b. All right, and then let's go with the log of a. The common log of a, let's suppose it equals some number r. It's got to equal something. And so that would mean 10 to the r is equal to a. Okay, now we're going to come on over here to this side and start with our statement that b to the p is equal to a. All right, and as I said, let's substitute a to get, all right, so we're not going to mess with the b to the p, so we've got is b to the p. We're going to replace a with, what can we replace it with? We can replace it with 10 to the r, it appears, okay? And now we're going to substitute the b, because we can replace that with 10 to the q. So we have 10 to the q raised to the p is equal to 10 to the r. And of course, we've already talked about this here. We have a power raised to an exponent, so that means we multiply the q times the p, and then we still have 10 to the r over here. So we have an equation that says 10 to the q times p equals 10 to the r. Well, the 10s are equal or the same, the bases are the same, so that must mean that the exponents are equal. So the q times p must equal to r, all right, which means that p is going to equal r divided by q. And let's see, the p we can replace, I'm going to substitute back and replace that with the log of a base b. The r, what was r equal to? That was the log of a. All right, so we got the log of a, and then the q was the log of b. So there we go, QED, quadratic demonstratum. We've shown that the log of a base b is equal to the common log of a divided by the common log of b. And what you need to remember is we chose to go with the common log. I could have done this proof using natural log up here, okay? And if I'd used ln for both the log of b, sorry, I need to be pointing with my mouse. So if I used ln up here instead of common log for both the log of a and log of b, I would have ended up with the natural log of a, write that in here, divided by the natural log of b. All right, so beyond a shadow of a doubt, this change of base property is true. Okay. All right, now I thought it'd be a good exercise just to kind of see how we could use some of these properties to solve some equations that you've already had some practice solving. So I'd like you to just pause the video, take a few minutes, and solve this the way you've already practiced solving an exponential equation, okay? Just to kind of help you get started. You know, when you look at this, we got to get to that 2x. That first thing to get rid of, I think, would be this 5, right? So we could have 1.36 raised to the 2x is equal to 12 divided by 5. And you know, if you want to get the decimal, you can. I think I'll just leave it as 12/5. But see if you can take it the rest of the way. All right. You will need logarithms, right, to deal with that 2x, that exponent, because you've got a variable in the exponent. Okay. See if this is what you did. Okay. Hopefully you got about 1.423. You know, we can change this exponential situation to a logarithmic one, where we take the log of the power with our base down here, and then that would equal the whole exponent 2x, right? That's maybe one place that sometimes students mess up. But then you just need to divide by the 2. I decided to multiply by 1/2, and you can plug all this in your calculator and get 1.423. All right. Well, I want to show you a couple other ways to look at solving this. You know, one thing that sometimes happens is instead of getting an approximate answer here with 1.423, we want to get an exact answer. And this right here would be an exact answer, the 1/2 times this log. You could just leave it like that and say that's my exact answer, because of course once you plug it in the calculator, you're going to have to round and chop, and then you're approximating. So that would be a fine answer to leave as exact answer, unless the question said we would like your answer to be only in terms of either, say, natural log or common log. So let's just suppose we were supposed to solve this and give our answer exactly in terms of natural log. Okay. Well, if that's the case, then what we could do here with this answer is we could come down and use that change of base property, right? We could rewrite this log of 12/5 base 1.36. We could write it as the natural log of 12/5, right, divided by the natural log of 1.36. And that would be an exact answer only in terms of natural log. Of course, one other thing we could do, if you might have noticed, we have the natural log of a quotient here. So we could rewrite this as the natural log of 12 minus the natural log of 5, all over the natural log of 1.36. Right? And if we wanted to take it just a little further, clean it up just a little more, we could say, well, it's the natural log of 12 minus the natural log of 5, and then we can multiply that 2 into the denominator and have it as 2 natural log of 1.36 equals x. And if you think about it, if you even wanted to, you could put that 2 as an exponent on the 1.36, but a lot of times we would leave it like this. Okay. Now, if the instructions had been right off the bat to say solve exactly, say in terms of natural log, ln, then one way we could approach solving this would be just to go directly into natural log. And a way to do that would be to just take the natural log of both sides of the equation. So the natural log of 5 times 1.36 to the 2x, that in parentheses, and then have the natural log of 12. You know, as long as we do the same thing to both sides of an equation, we are fine. So we can do this. And I'm noticing now, I want to break this down because I need to solve for x, and I'm noticing I have a product here. I have 5 times something. So we can use that property, the log of a product, and say, well, this would be the log of 5 plus the natural log of 1.36 to the 2x equals the natural log of 12. Okay? And then at this point, we can apply that power to an exponent property, right? We have the natural log of 1.36 raised to the 2x. That 2x, let me use a different color here, but that 2x, circle it, can come out to the front of what we're taking the natural log of. You know what though, maybe before I do that, let me subtract this natural log of 5 to the other side. That'll make things look a little better. Minus natural log of 5. So we'll have the natural log of 1.36 to the 2x equals the natural log of 12 minus natural log of 5. All right, and now maybe it's a little easier to focus on the fact that we can take this exponent here and bring it out to the front. And as we do, here I'll just go on to say, so we'll have 2x times, come back and have natural log of 1.36 equals natural log of 12 minus natural log of 5. And as we do this, my question would be, what kind of equation do we have now? If you look at it closely, we actually have turned this equation into a linear equation, all right? We have 2 times the natural log of 1.36, I'll put that in parentheses, times x equals the natural log of 12 minus the natural log of 5. This is very similar to, here I'll use a different color, go back to purple. So it'd be very similar to having something like 2x equals 12 minus 5. You know, we're basically going to do the same thing to solve it, right? We're just going to divide to get x by itself. So we're just going to have x equal to natural log of 12 minus natural log of 5, all divided by 2 times the natural log of 1.36. And so there we go. We have the same answer. There's one more thing we need to do. Let's now check and see if this answer gives us, what did we get before, the 1.423 answer that we were getting. So let's go over to our calculator. Here you can see I plugged in the old version of our answer, and let's try our new version here. Now we need natural log. So we need the natural log of 12, come outside the parentheses there, minus the natural log of 5. All right, and then that's all over 2 times the natural log of 1.36. And let's see if we got it. Yay. So I hope this video has helped you become more familiar with the properties. Remember, there are 4 of them, right? We've got the product property first, then the quotient property with the minus there, and then the power property, which is really kind of an exponent on the power, the u. And then we have the change of base property. The ones you're probably going to use the most would be the first 3, but occasionally you'll run into the change of base property. It hasn't become quite as important recently, at least in pre-calculus classes, because our calculators now can handle other bases. But back when I was in high school, the only kinds of logs you could take were either common logs or natural logs on a calculator. So you had to use this this change of base property if you had a log, like what we were doing down here. If you had to take the log of 12/5, 1.36, in high school I would have had to plug it in as natural log of something over natural log of something. So anyway, I would recommend that you do get some practice with these using the Khan Academy problems that I'll have go with this video.